As he mentioned, my name is Georgia Ewen-Campen. I'm a senior associate at Heinches. We're a firm of architects and engineers working as facade and curtain wall consultants in New York City and San Francisco, and we work from concept through construction. Today I'm going to present the facade design for the Nike House of Innovation in New York. The flagship store, it's on 5th Avenue and 52nd Street and opened last November. The original facade design is Nike Global Design with Callison RTKL as the architect. Sealay was the facade contractor on the job, and Kricursa made the glass. Heinches, ourselves, we served as the facade consultants. The site here was the podium, first through 6th story on 5th Avenue and 52nd Street, as I mentioned. And the idea was to raise kind of a typical 1 to 2 story storefront to the full height of the 6 stories. The design intent was to represent motion, to be a billboard for the brand's identity of speed and athletic movement. This is an early study which involved mapping the movement of a runner, measuring it, and kind of mapping it directly onto the facade, mapping that data as an image. The designers wanted the facade to be more dynamic than just a flat image. They wanted glass to provide transparency, limited and distorted transparency to the store experience within, but they wanted the facade to be activated. They aimed not to just represent, but to embody motion. The idea was how to do this with the glass. So we know that glass can be molded and shaped into many forms. There's lots of architectural examples of curved and textured glass that were looked to as precedents. And from that developed Nike's intent. They wanted to create a lenticular view through the glass with constantly shifting reflections, refractions of light, a tight membrane vibrating with energy as people move around, through, and inside the facade. So there were 2 scales of patterns on this facade. The double curved geometry of the slumped waves, which tapered to a flat perimeter, was discussed as the macro pattern. This was enhanced by a micro pattern of lines, providing a finer grain of texture on the surface of the facade. The inner light would be flat to allow for low-E coating, but also for the application of graphics behind in the future. And as this got started, the idea of translating this onto a facade in a building presented a number of challenges. So it wasn't a stretch to think that the glass could be physically made into this shape, but to implement it on a facade, to feel comfortable with the engineering and everything, and to have someone kind of sign off on it was more of a challenge. Some of those challenges included lack of established rules for engineering glass with the surface disruptions, as well as the use of annealed glass necessary from the slumping process, which would be more vulnerable to breakage from thermal stresses. The flat inner light expanded options for the low-E coating, and as mentioned, for graphic application, but it meant a larger volume of air between the lights, which would increase climatic loads, which I think I heard a couple other presentations talking about those challenges today. As the air expands and contracts throughout the year, that larger volume of air can create issues. In addition, there was the typical issues of consistency, visual quality of the glass. And then we had the schedule. So this all had to be accomplished on an accelerated retail project schedule. So we got started. The engineering analysis started with geometry from the design team. See here. Heinches used that 3D geometry for preliminary engineering of the slumped glass, checking for stress and deflection to confirm the viability of the architectural design. We looked at different reductions in thickness, different assumptions for the areas where the glass was to be carved. We also looked at thermal stress on the glass, with the worst case being a hot differential temperature between the center and edge of the glass in the summer. And then evaluated as well the IGU performance under the climatic loads. We calculated equivalent thickness of monolithic glass that would have the same stiffness as this very stiff laminated outer light. Approximately 1.5 inches equivalent of glass was used to check the deflection under climatic loads of the inner light, which being much thinner would do most of the deflection. Wanted to make sure that the stress on the edge shield was okay, and also that the two lights wouldn't touch under any of the expected conditions, including when you incorporate in all the glass tolerances. So as these engineering analyses were continuing, kind of once we showed feasibility, we knew with the schedule that it was important to bring on glass fabricators early. And so at this point, Precursor was contracted to kind of join the research and development, starting with a selection of samples to look at how to create the micro pattern and how the macro pattern could be joined with that to get the desired effect. So Precursor, in their factory in Barcelona, began working on a number of trials. This is a view of the micro pattern, which was created by carving shallow grooves on the #1 surface of the glass, carving and polishing with a CNC machine. And then this is one of the first photographs we saw of a small size sample of this first prototype where that carved glass was then gravity slumped on a mold to create the waves and come down to the flat border at the perimeter. I think when this photo was sent, these initial samples were reviewed through photographs and conference calls. There was everyone kind of let go of the breath they'd been holding and thought, okay, it can happen. We can make this project. It began to feel real, but of course there was a lot more to do. The next small sample done by Precursor was to create an IGU sample. So here there was a laminated outer light. There was a flat inner light. I think in this sample the inner light was actually laminated as well with a flexible edge seal. And then we moved on to the next round of visual mock-ups, which was full-size, project-size IGUs that were reviewed at Precursor's plant by the design team to make the final decisions about the pattern and location of the microtexture, as well as the slump shape. The outer light, at this point, we settled in on the glass makeup. It's 10 plus 10. The outer light is carved, as I mentioned, with about 1 millimeter deep grooves, and they were 20 millimeters wide. And then the inner light is heat strengthened with a low E coating on the #5 surface. From these samples, the final geometry and of the glass was determined. Some of this came from the design team's refinements, and some of it came from the fabrication requirements and limitations. So the adjustments in the width of the flat perimeter band, where the edge seal would lie, as well as the height of the slumped waves. And these revisions were then taken back into the analysis and checked again to make sure that the structural acceptability of the glass form was okay. It was acceptable. So at this point, there was actually a decision made to make uniform the glass sizes, largely to somewhat for cost and to limit the number of molds required for the glass. You can see here there's 4. Oops. Well, you can see there. But there are 4 atypical lights right there. The rest of them are all typical. But the other thing this did was actually make the facade stand separate from the structure behind, and it divorced the lines of the facade grid from the floor levels behind. It was at this point, with this design finalized, CLA was brought on as the facade contractor, and along with Larson Engineering, they were the engineers, the final engineers for the full facade system. So here, image of this facade, the structure was steel framing, mullions and transoms that were hung from the roof up here. Coming down, they were connected laterally at the 1st, 2nd, 3rd, and 5th floors. And there's actually there's the entranceway, as I mentioned before, just has the 4 unique lights of glass. That I guess here that you can see the glass units are about 2.4 by 4.1 meters. And the wave pattern, the angle, is 23.5 degrees, which is the same angle as the Nike swoosh. And also, the spacing was designed to allow that angle and to continue the lines across the entire facade between panels. The glass was pre-glazed. You can see here the kind of the design, pretty simple pre-glazed to aluminum glazing adapters, and then with a toggle system designed by CLA attached back to the steel framing. And this development of the facade system provided information that was fed back into the glass analysis. So here is a deflection analysis of the framing, of the steel framing. And you can see highlighted in yellow a couple locations where, due to the locations possible for anchoring back to building structure, we had differential deflection. And the glass, we needed to make sure to balance kind of the stiffness of the mullions with the inherent stiffness of this glass, and to make sure that the glass could accommodate the differential deflection of the framing without excessive stresses. You can see some of the analysis here. We had made assumptions, particularly about the carving in the glass during the engineering. And to validate some of that, early on there was material testing done. 4-point bending, was the EN 1288-3. 360 by 1100 millimeter samples with smooth ground edges. And they were all fired flat with the slumping kiln with the same time, temperature, duration that was expected for the final project, for the laminated glass. And the idea was to test and see how it related to typical flat glass. And as expected, the carved glass was slightly weakened by the carving, a larger reduction in strength when the carved surface was in tension, but it still performed structurally. And this was encouraging. I think the assumptions that were made during engineering proved to be pretty accurate. But at the same time, further testing, in order to feel comfortable, further testing of actual project glass was required. So 5 full-size pieces of just the outer light, so just the laminated 10+10 carved slumped outer light, were structurally glazed to the aluminum glazing adapters, and attached, you can see here, there was a test chamber at CLA's facility in Germany. It was tested for structural and for thermal loading. This is the test setup for a thermal stress test, where a heat source was put in the middle of the glass, and looking at the temperature differential across the glass, the expected, based on calculations, the expected differential between edge and center of glass was about 20 degrees Celsius. The idea was to try to test to 2 times that, and then also to try to test to breakage. However, even achieving 120 degree differential between the cold edge and then the warm center, which was as high as the equipment could get, there was no breakage. So gave everyone another level of comfort with the thermal stress. And then also on that chamber, the glass, there was a typical structural loading. So design and 2 times design, pressure and suction were tested. The deflections measured, everything kind of checked out with what the models showed, about 6 millimeters of deflection under design wind suction. Which was, but we wanted to test and understand the ultimate strength of these and test 5 lights to breakage. The load to do that was greater than could be handled by the chamber. So CLA created this vacuum box in their factory. The light was sealed to it, and air pulled on it. And here I have just a couple stills from a high-speed video recording. So you can see, eventually it did break. And appeared that the location of the kind of break origin was near the edge, which was validating the previous engineering analysis. And there was quite a high safety factor based on what was actually breaking and what we were finding with the stresses on the project. An assembled IGU was also put in Sile's facility and reviewed by the design and construction team to establish acceptable criteria for the quality control of the production glass. There was a QC inspection checklist established that Sile used to check each completed IGU. The issue of the climatic loads and the airspace came up again here. One of the early sample, there was damage caused when the inner and outer lights had touched, the airspace being too narrow in the middle. And fabrication methods were established to ensure that that gap was consistently wide enough. Every IGU was checked both at Precursor and then also again by Sile at their facility. And Heinz just made several inspection trips as well to verify those procedures. Here you can see the IGU glazed onto the glazing adapter. There's also a stainless steel trim, which is part of that. And then they were shipped to site. So this is the scaffold going up on site. Less than a year after the glass design really began. You can see here the scaffold is both for privacy, but also construction on Fifth Avenue in New York is very tricky. You can't use a crane. Well, you can't close the street or the sidewalk. So the scaffold fully enclosed the site, and work was conducted behind. Once the demolition was done of the existing wall, you can see the steel framing was installed, anchors, and construction access was done from either the inside, which you can see with large atrium. There pretty soon was not much access from the inside, and from the scaffold. You can see on the right here, very narrow gap between the scaffold and the mullions, which was in that space that the glass units were lifted into place and installed. So they used a manipulator to lift the glass, position it vertically, and then used a frame that was suspended from a monorail at the roof to lift the units up into position, to put them in place, and then they were attached to the steel frame with toggles and sitting on the dead load chairs on the horizontal transoms. There were final adjustments were made later as all of the weight from the glass, the final settling of the framing. Once almost all of the glass units were installed, the scaffold was taken down. And here, the completed store. This is November of 2018. It opened last year. The innovative enclosure was successful. The translation of the brand identity into a unique facade, embodying motion, performance, and innovation. The macro and micro textures create shifting reflections, refractions, as the glass exists both as a lens and as a surface. The perception of the facade materiality, color, and transparency change with the viewing angle, the weather, the sky conditions. And the facade is experienced very differently during the day than it is at night. During the day, the view from the exterior emphasizes the slumped glass shapes with the reflections of the light. From the inside, the glass appears much flatter in that light, but the carving is much more apparent. I think this image shows the motion of the city outside, expressed through the distortion and the elongations of the transmitted image. A corner view here shows similar effects, but then you look at the same thing at night, and the effects change. Here's an example. This is showing you kind of divorcing the facade structure from that of the floor plates, emphasize the facade as its own element. Yet it speaks to and helps to celebrate the atrium and the stairs, which run at the same angle as the pattern on the facade. And then here, just an example of something I liked on site, some unanticipated experiences. You can see in the video on the right, the reflections from some of the video signage is really captured by the texture on the glass. So all in all, I feel it was a pretty successful example of how initial concept to embody motion can come to exist as a dynamic building skin through innovative, accelerated process of design, research, engineering, sample review, testing, fabrication, and installation. Thanks.
Great presentation, Georgia. Are there any questions from the audience?
Great presentation, great building. You mentioned a firm in Barcelona. Could you explain a little bit further where the materials were being produced, or?
Sure. Craig Hurst is the glass fabricator in Barcelona. So they did the slumped glass, the carving and slump glazing there. The steel was by CLA, German facade contractor. I think the steel was fabricated actually in Poland on this project.
Did you ever consider of producing the material in the U.S. Sort of in order to support the idea of sustainability?
I think on this project with the glass in particular, it was really a matter of finding somebody who could work with us to do the design and the research and development, because it was really trying to develop a new product, essentially. And we didn't find that in the U.S. on this. So yeah, I wasn't.
How did you come up with the firm in Barcelona? Had you worked with them before, or?
We had, yeah. We spoke to several curved and glass providers in Europe and some in the U.S. as well. But this was the one that kind of we did initial discussions and even a couple initial samples with a couple firms. But as we saw, they kind of came through with the glass, and they have a long history of doing this kind of product.
Does Nike have a glass department like Apple has?
I don't believe so.
Okay.
They have a design department, but not a glass department. Not yet, at least.
Okay, thanks.
Thank you.
Thanks.
Hi there. Did you like what you just saw? If you did, why not like the video? Drop us a comment below, as well as share the video with others, since GPD is all about sharing. And to receive more videos in future, subscribe and don't forget to click the bell icon for notifications. Ciao.